Dr. Hoppie, we're glad to have you with us today, and we're interested to hear what you have to tell us, so go for it.
Okay, so my story in Sleepy Eye starts 5 years ago, I think it
just
was,
about.
when we were asked at the university, could we contribute any information, could we be of any assistance in helping you all keep from having to go back into Lake Sleepy Eye and suck it out again, get the mud out of the bottom of the thing. We weren't sure how much mud was accumulating in the lake. We didn't know how it was getting there. So instead of actually proposing to everyone here in the room in the Sleepy Eye to go in there and take cores from the lake, what we proposed to do was actually take a look at the feeder system to the lake. Let's figure out whether or not the filter to the lake is working properly. And to do that, what we wanted to do was take a look at the actual slough, the wetland, just on the east side of Highway 4, to ascertain how much sediment, how much nutrient is washing into that thing from the surrounding farmland to the north and to the east. How much is washing into that wetland from the nearby overland contributions, like the lawns and the farms that are right next to the thing, and how much is coming from a little bit the same sort of source, but further away, like the city. How much is coming in from the city? Then, as shown here by that blue circle in the lower left-hand corner, how much leaves? How healthy is this wetland? How healthy is this filter to this system? Because it turns out that most of that runoff, most of the contributions to Lake Sleepy Eye are going to be passing through this system here. So if we can figure out whether this system is operating properly or whether it's in need of some serious help, then we can determine or give you some information about how it is to better address the overall quality of water in Lake Sleepy Eye. So what we wanted to do was ascertain the amount of contributions to that wetland from the neighboring farmland. How much is coming from the city? How much is actually leaving that wetland and going out into the lake? That was the goal of our project. So we set this thing up at the very beginning of 2021 with a number of pieces of equipment. The primary piece of equipment that we're using to do our measurements to come up with this answer is that thing in the upper left-hand corner there, an ISCO automatic water sampler. That's a 6712C for those of you in the crowd that care about 6712s versus 6715s. That's a 6712, which essentially is an automatic pump. That's all that the thing is. It's a pump, though, that has built into it a computer control board on the top to which we can attach sensors so that it will pump when it rains. It will pump when the water rises in the ditch. It will pump when that rising water in the ditch turns terribly muddy. We can tune this machine to take samples at whatever feature it is that we wish to ascertain, to know better about the system. For us, it was all about the water. We wanted to know when was the water entering that wetland? When was the water leaving that wetland? Then, when the water is coming in or coming out, let's take samples of it. And that's what happens on the inside of that machine. It's essentially a giant bottle. And we can tune that computer on the top to take a water sample every 20 minutes or every 10 gallons. We can tune it to whatever the parameter is that we so choose to make sure that we get a representative sample of the water that's washing into the wetland or leaving the wetland and going out into the lake. That's the heart of the business right there. Now, of course, if we're talking about rainfall and runoff, we better be having a close eye on the weather itself. So we had a weather station that was installed. It was at the top of St. Mary's High School for a little while. Then I just moved down in Middlefield, but we're watching the weather minute by minute. How many inches fell? When did they fall? What was the intensity of the rainfall? We wanted to keep track of all that information as well, because it's important to us to understand why our machine was filling up with water, Why was there mud washing into the wetland? The machine itself always has to be physically calibrated. So I've got a picture of some students over there on a big pipe. That's actually much closer to Arlington, Minnesota. But nevertheless, we have students out there in the field physically measuring the amount of water that's going through the ditch, through the pipe, through the places where we're measuring the water, so that we have the hard physical. It's not just an instrument. It's not just an electrical signal. It's actually tied to something physical that we did in the field to know exactly how much water is moving at any one time in the wetland. I'll show you in a little bit that we also flew a drone over the thing. Because why not? You can fly a drone. Why not fly a drone? So we flew a drone over the wetland in a couple of different instances, and I'll show you the results from that as well, because we wanted to get that bird's eye view. We wanted to see what everything looks at all simultaneously. When you're down in the mud and you're in a sewer pipe, it's hard to tell what's happening on the other side of the wetland or what's happening 300 yards away. So we needed to be able to see everything all at once. So that's the advent or the add-on of the drone to our study. Finally, then there at the bottom, a pair of infiltrometers were planted. Essentially, it's a giant double steel ring, and we go out there into the wetland and we plant them, because what we didn't know was, that's something we had to figure out, was we couldn't account for all the water. We would measure all the water washing in, we would measure all the water washing out, and the two numbers weren't the same. They were very different from one another. Why is that? So that was a secondary scientific experiment that was undertaken after the fact. After we were already here, we thought we had done everything that was necessary to create a water balance for your wetland, and we were missing water. We were missing 100%, well, 50% of all the water. Where did it go? So I'll describe to you in just a little bit that experiment as well, and what we found out from that. Now, the backdrop to everything that I'm telling you, everything, and I'm going to tell you what to do with your lives. No, I'm also going to just make sure that you understand all 3 years of analysis were completed during the drought. Drought, and then drought, and then drought again. The drought isn't just in that you don't have as much flow. It also changes the dynamics of the flow as well. So, for example, when you have lower flows, you're going to have slower moving water. The high water is the fast flowing water. The fast flowing water is the energetic water, the water that can carry more mud, the water that could be more destructive. We had low flows. And when you have low flows, you're going to come up with one set of numbers that describe low flows really, really well, but that's not the whole picture. That's not the entire part of the story. I'll describe to you a little bit later how we can take our low flow numbers and maybe project them and start making some estimates about medium flows and higher flows. But for the numbers that I show you now and the story that I'm telling you, please know this is because it was a drought, and then a drought, and then a drought again. So here's the first of the charts that I'm going to show you, the first of the charts that's probably alien to most all of us, and even me originally, but now they tell us quite a bit of the story itself. The up and the down on this chart, the vertical is going to be the flow of water. It's called discharge here, but discharge is just the name that us scientists use when we're talking about a volume of water per unit of time that's flowing through a pipe, or through a ditch, or through a river channel, or whatever the case may be. We use the word discharge. The scale over there, 5 cubic feet per second. Remember, every cubic foot has got 7.5 gallons of water in it, so you might think in terms of gallons, but scientists always deal with cubic feet, or, dear God, there are some scientists always deal with liters. Liters, please, why bother? So we've got this cubic foot unit over here, 5 and 10, and then on the x-axis, moving from left to right, is just the time. April of 2021, and then you can see April of 2022, April 2023. Notice there are these big gaps in that line. The line also changes colors. But, you know, we're just monitoring during the quote-unquote flow season. So if the thing is frozen up, if the thing has got chunks of ice in it, we're not making measurements. We're only trying to measure the water that's moving through the system, washing into the wetland or washing out of the wetland. This particular graph is from the northeast corner of the wetland, so this is essentially just the farmland. Just the farmland runoff and contributions from the shallow underground into County Ditch 45. So this essentially is all the water that moved through County Ditch 45 in 2021, 2022, and 2023. Notice that, you know, it's really very spiky because it's highly responsive to those rainfall events. So we get a big rainfall, and there's going to be this spike in this amount of water that's flowing through County Ditch 45 and into the wetland. The other thing worthy of note on this chart, well, first of all, 2022. We should just rename all of 2022 as Why Bother 22, because it was so dry. It was dry the year before, and we didn't get the makeup rain that we needed to move things back to normal, so it just stayed dry. So you'll notice that the green in the middle there doesn't look like much, because it wasn't much. There just was no flow. There was nothing really to move because we didn't get a good precipitation event during that year that would cause runoff off of the farm fields that are north and to the east of the wetlands. 2023, you notice, oh boy, there was really a good May. That's what a hydrologist loves to see. The really high flows right there in May 23. But then somebody turned the faucet off. The rains dried up. They didn't come back with enough ferocity, with enough frequency in order to keep the flow going effectively in 2023. So that's our year. Now let me help you with that number on the vertical scale there, the 5 and the 10, by showing you a picture here. See, does it play like that? There we go. You're wondering what a cubic foot per second actually looks like? That ain't it. That's 100 cubic foot per second coming out of the end of that pipe. The cubic foot per second is what you see essentially dribbling off the bottom of the pipe over there. It's nothing. A cubic foot per second in the Minnesota River, on a good day in the spring, the Minnesota River, they'll have 110,000 cubic feet per second of water flowing. So we're talking about the type of flows that I'm showing you on the charts being essentially 99% lower than the Minnesota River. 70 to 80% lower than your Cottonwood River. These are very small numbers that I'm going to be showing you. Again, it was a drought. I mean, I don't know what numbers I could show you because it was drought conditions. And when we have drought conditions, we have these low flows. So essentially, everything that I'm going to be showing you is going to be based on just the dribble off of a pipe that might be leading off from a nice big rainstorm somewhere, sometime, some way. So we measured all that water. Those machines took water samples. And this is Max of the man collecting the water samples and running them to, where did you take all these water samples?
New Ulm,
MBTL.
Yeah.
It's a certified laboratory. They've got great numbers. They've got chemists that worry about having great numbers. So they've got all of our results from every year, every rainfall event. Whenever the machine was turned on, a water sample was collected and it was taken to New Ulm and tested. Tested for the amount of sediment that was in the water, the suspended solids. Tested for the amount of phosphorus that's in the water. Phosphorus is a limiting reagent, nutrient in the environment. Essentially, plants and things around us can always come up with all the carbon they ever need. And often nitrogen is just around and all that they ever need. But phosphorus is this rarity thing out there. They gotta have it. We need it as well. There's gotta be phosphorus, but phosphorus just doesn't show up in the environment. It almost has to be applied to the environment in order to make it show up. So we measure that because as long as there's phosphorus, there's going to be some nitrogen in most instances, and there's also going to be carbon. So there'll be the growth of algae, there'll be the growth of plants, there'll be the potential for lower water quality. So we want to track that phosphorus very carefully. Nitrogen is on there. We put lots of nitrogen on fields. We use lots of nitrogen in our homes. We've got lots of nitrogen around us. And nitrogen also leads to algae blooms. Nitrogen also leads to lower water quality, so we wanted to measure the water quality. And to do that, we needed to include nitrogen and in phosphorus, and also the sediment, the amount of mud washing into our little wetland. So you can see we've got the county ditch samples on the left-hand side, the storm sewers and the main lake, or what's draining out into the main lake, or what's leaving the wetland. Those are just samples from 2021. We've got samples from 2022. We've got samples from 2023. Max, I don't know how many, 20 samples or so this past year that you're responsible for, running back and forth. Anytime that there is an elevation in the amount of flow in the ditch, or in the storm sewer, or leaving the wetland out into the lake, anytime that thing went up by 10%, we grabbed a water sample and we took it over to the lab and had it tested. So what you can do when you have these lab results and the amount of water that was flowing through there, we can turn that into pounds. We can tell you how many pounds of sediment washed through the ditch and into the wetland. We can tell you how many pounds of nitrogen washed out of the wetland and into the lake, because we've measured how much water there is, and we measured the concentration of this contaminant in that water. You put those two together, you got answers. So that's essentially our goal. How much mud washed into the wetland? How much mud washed out of the wetland? That was one of our primary goals, and this is what tells us those numbers. By measuring the water constantly and grabbing all these water samples, we're able to come up with that defensible number of numbers that we included in our result. So, one of the things to keep in mind when we start comparing what washed into the wetland from the farm, what washed into the wetland from the city, and what washed out, are a couple other factors that we hydrologists have to keep in mind, and one of them is simply this factor called abstraction. If there's something on the ground, that something on the ground is going to absorb some of the water. So there's going to be some of the water that gets stuck on a leaf or a stem before it actually hits the ground. Some of the ground itself might be really rough and torn up, and a few of those drops of rain might actually hit that rough surface and get stuck right there. Won't soak in, won't go down into the groundwater, won't run off, it's just stuck right there. So that abstraction factor is something that we try to assess by having measurements made and doing some guesswork as well. But we come up with this idea that somewhere between a third and a first inch of any rainfall on that farmland, it doesn't go anywhere. It's stuck on that farmland. And if you've got a mature crop on that field, you've got corn in canopy, that number is going to be even bigger than 1. So this is that average number, the 0.3 to 1 inch of any rainfall event is potentially, none of that ever leaves the farm field. It's all stuck on the plants or the soil itself up there on the farm field. Another thing worth mentioning about that farm, the farmland around the place in north and east of the wetland is, damn, it's flat. You got some flat land here, people. So, its average slope is 0.00% grade. So that's nothing. It's really flat land up there. So you got a lot of precipitation on the flat land. It's got to overcome the fact that, it doesn't have that driving potential. It doesn't have its head trying to push it downward and into the ditch in order to get drainage. It's just happy being on that flat land. It also has a lot of capacity to fill up the dry soil beneath the surface. In the northeastern part of that wetland area and a little bit further away, your water table is 45 feet down. I mean, you have some deeper water table in that part of the country up there. So, and in that 45 feet, you've got more than, or at least 35% of all those feet of soil are just open space, pore space, where you can put more water. So a lot of the rain that falls that doesn't get absorbed by the plants or the soil on the surface just goes into the ground and gets absorbed by the ground. It will come out eventually. You can override these systems when you get that bigger rain that then suddenly keeps everything on the surface wet. And it doesn't have the time to percolate down into those pore spaces, down into the underground. So there are those opportunities for it to actually turn into runoff, but it takes some rain to do that. It might take an inch or more of rain in order to get that sort of runoff, something that we would actually be able to measure, which is that same chart that I showed you previously. Those are the cubic feet per second of discharge that occurred in 2021, 22, and 23. The numbers are pretty small, and we're not surprised, because that farmland was built to absorb the water that falls from the sky. That's the way that it works. So, as I mentioned previously, we do have the flows measured, and we have those concentrations from the chemistry measurements. You can put those together and actually calculate pounds. So I've got some pounds to show you, and this is a repeat of numbers that I showed you in 21. I got new numbers too, but first a repeat of the original numbers that I showed you, just to give you some idea. So from the farmland in 2021, there were 8 tons. 8 tons of mud that washed off the fields and into the ditch, past our monitoring point in the ditch and into the start of the wetlands. About 8 tons of mud. Is that a crazy whack number that is way out of line? No, that number is tiny compared to the pounds per acre that are typically associated with other parts of southern Minnesota. So again, there's a lot of abstraction on that soil. This soil is very flat. There's a pretty thick vadose zone, or zone of open pore space. So a lot of the water gets stuck on that land, so we're not surprised that the total amount of flowage down here at the bottom is only around 24 million gallons. Is 24 million gallons a number that you all should be worried about? Mankato makes 26 million gallons of water a day to give to its people to drink and flush its toilets. So this is a tiny, tiny number. Is there anything else worthy of note on there? Also, the nitrogen number is far below the typical nitrogen number for southern Minnesota farm fields. So it's looking good in 2021. Now granted, this is a drought. Gotta keep emphasizing, this is a drought. During the drought, a small amount of water washes into that wetland from the farmland. During a drought, a very small amount of sediment, a very small amount of phosphorus, and a very small amount of nitrogen washes into the wetland. This is 2021. Remember, 2022 is even drier. 2022 is even likely to have even lower numbers, and so it does. It's got lower numbers. Half of the 2021 number is the pounds of mud that washed into the wetland during 2022. 2023, the pounds come back up. Remember, May 2023 was a wet month. We got that water. We washed everything that had been washed into the wetland in 2021 into that wetland in May of 2023. But then the water turned off. The valve was turned off. Things got dry. So then ultimately in the end, the annual number for 2023 and the annual number for 2021 are about the same. And in all cases, this is low. These are all low numbers. You are not, for the camera, you are not getting substantial contributions of mud or nutrient to the wetland from that farmland in 2021, 2022, or 2023. They are 3 drought years, but during those drought years, that farmland is doing putting nothing to that wetland. So let's take a look at the city. You'll notice, first of all, there's a lot more spikes on this graph than what I was showing you previously. We are positioned at the end of that storm sewer, the storm sewer that is underlying much of eastern, northeastern Sleepy Eye. So we have a lot of drainage that's coming into that thing. I don't know the percentage-wise of the city that's underlain by that particular storm sewer, but we're there. It's a big sewer, and we are watching the water flow through that thing with our sensors and our pump pulling the water out of the thing. That our sensors are indicating numbers here. Remember, on that last graph I was showing you, I was lucky that the number ever hit 5. And here you can see that the number is going up to 10 in more than a couple of cases. So we're getting like double the amount of, at least, cubic feet per second. But then as written over there on the right-hand side, this is very flashy. This is the stuff that falls on your streets, the stuff that's on your sidewalk, the stuff that's on a roof and then comes down a gutter and then is on the sidewalk and then is in the street and then is in the storm sewer. This stuff just flashes through here and goes very, very quickly. So although these numbers are much higher, they're not as wide. So the total amount of water isn't necessarily all that much more than what I was describing to you previously. It just appears to be at a lot higher rate. So the numbers that we generate when we start taking a look at that total amount of water flow and the pollution inside of it are these types of numbers here. First of all, notice that this is an urban setting, so we've got this very high percentage of the total rain that falls on your city that actually is something we can meter or measure in that storm sewer. So we're getting 88% falls from the sky actually showing up in the storm sewer. That's city, that's urban. That's what happens in Minneapolis and St. Paul, and yet it's still happening out here in Sleepy Eye. Again, it's just the mechanics of the system. It was very dry, and the lawns weren't necessarily going to absorb that first bit of water that fell on them, so it just turned into runoff. It turned into the stuff running down the driveway, across the sidewalk, and into the storm sewer, and then we measured it. It was a little bit on the dirty side as well. Notice that my number of pounds there has climbed from 19,000 or something like that previously. So it's dirtier. So it's picking up the mud on the sidewalks. It's picking up the gravel that was dropped on the street, and it's mobilizing that, moving it into the storm sewers, and then washing it through. It does have some fairly low concentrations for the nitrogen, but this is just what we do to our lawns. We feed our lawns. We cut the grass, and the grass goes onto the sidewalk and out into the street. When we measure that nitrogen, it's because that part of those grass clippings are already decomposing, and some of that nitrogen is now in the storm sewer where we're taking those samples. So we do have another set of numbers here for you that are not as... that farmland is a dream come true. That stuff was absorbing everything on it. Nothing was running off of that thing. That was gorgeous. The city is just doing what cities do. So this is not out of the ordinary. This is not, like trying to find blame. This is not trying to say, you guys got to fix this thing. You got to fix it now because it's broken bad. It's not like that at all. It's that this is just normal. This is very normal for what a town does in its runoff. Adding then in 2022 and 2023. What we see is, again, the numbers are just the same. It's just a city being a city. I do have, you'll see that I've written myself the note down there. That's a low number. Why is it only 54% of the water is running off in 2023, whereas we were getting numbers much, much higher than that, like 88 and 84% in 21 and 22? That's science. Science is going to have to look at that. Science is going to have to tear apart why it is that we've got that slightly lower number there in 2023. But all things said and done, these are just city numbers. Nothing to be overly concerned with respect to these numbers. They look just fine. You'll notice that you do have some higher values that are highlighted over there when you start taking a look at the yield of things like the sediment or the nitrogen in that case like that. But again, those are not out of this world numbers. If you remember, I think I had on the previous slide, 10 to 30 are very normal. And here you are, you got 20. That's right in the middle. So this is very normal conditions, what you had as the runoff from your city at this time. Now, let's take a look at what leaves the wetland. Maybe some of you have seen what was our station. Max took it out last fall, but our station, which is right over there on Highway 4, that one outlet that leads from the wetland into the lake proper. We had sensors in there, we had sample tubing in there, we were collecting our water samples and giving you this set of numbers. First of all, notice that the flows, they're not all the way up to that 5 and 10 like you saw on the city. They're not all the way down at 0 like you saw at that farmland. We're somewhere in between those two. So we're taking some of the contributions from the city, those higher flows. They were flashy, but they were higher flows, and now we're slowly bleeding some of that water out of the wetland and into the main lake. It says removes 90% of the sediment. Let me show you those numbers. They're genuinely impressive. So if you remember, we had from the city in 2021, we had 27,000 pounds of sediment. From the ditch, we had 19,000 pounds of sediment. How many pounds of those sediment actually leave the wetland and go out into your main lake? 1,000? Remember, it's 19, that's like 30,000 when I'm doing the math really quickly in my head, is how much washed into the wetland. And less than 2,000, well, just over 1,000 is what leaves the wetland. Wetland's sucking it all up. This wetland is absorbing everything that gets put into it. This is drought conditions, but during these drought conditions, that wetland sucked up everything. It absorbed everything that was put into it and said, give me more. Because I'm not full up yet. I'm not going to start moving any of this stuff out into your main lake because I still have the capacity in my wetland for all of this stuff that you're giving me. It's dramatic. 2022, 2023, it's the same story. For all 3 years that we watched this system, that slough sucked up everything that was put into it. Giant, giant reductions. How big are the reductions? Flipping ahead. It sucked up 96% of all of the sediment that was washed into it. It sucked up 95.6% of all the nitrate that was washed into it. It put away more than 75% of all the phosphorus that was washed into that wetland. This is phenomenal. There are engineers that build stormwater detention ponds and dream of these kind of outcomes. I think, this is adding, I'm just supposed to show you the results and not do my interpretation. I think it's just the size. This thing's massive. This has got 30 acres of open water. It's got 30 acres of cattails around the outside of it. This thing is a huge sponge on the edge of your city and at the end of that farmland. It's doing what a huge sponge is supposed to do. It absorbs everything that's coming at it. It's reducing the total water by 50%. It's reducing those nutrients by greater than 70 or 90%. It's a good day. That's a happy day. That makes water planners very, very happy when they see a situation like this. Now, we weren't able to count for all of that water. Some of the water just apparently disappeared from the system. So one of the things we want to do is make sure that we're tracking, doing our science correctly and looking at all of the leads. Where are the possible places where we might have had some water enter the system or be removed from the system that we weren't watching. So I've shown you this picture once before, and it might not show up all that clearly for anyone else other than the guy that knows what he's looking at. But there's these dark spots. Dark, 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 dark. And that's an infrared picture of your wetland. infrared picture that was taken off the drone. So we're at about 400 feet of elevation, looking straight down on this thing. There's, oh my God, I don't remember what there are. I think there's something ridiculous like 40,000 pictures that are all stapled together to turn into just this one picture that you're looking at. Because every picture is just this big. It's just a tiny, tiny little picture of the wetland itself. So what we're able to see, because this is infrared, is temperature. And where you have darker colors, you have lower temperatures. And why is that wetland having cold temperatures in those circular shapes, in those two different positions? It's the groundwater. It's the water coming up out through a spring that has a lower temperature. So consequently, we do have some spring contributions to that wetland. Why does that matter to anybody? Because it's going to keep your wetland wet. When an object like a wetland is wet, it's going to be a better filter. It'll be a better operating absorber of additional water, especially the sediment and the nutrients that wash into the thing. So having the springs operating in this wetland makes that wetland, which is a great thing to begin with, an even better thing. It's a great feature to have in your wetland. Now, we did have the meteorological station set up on top of the school, and we were measuring things like daily temperature and daily humidity and daily wind speed and everything that you needed to do. So that we could track for exactly, or knowing exactly how much water is physically being evaporated from the wetland every minute of every day. So we came up with those calculations as well. So they're kind of listed for just 2021 down there at the bottom. Like, for example, we have 10 million gallons of physical evaporation. In order to make the math work, beginning to end, we would have had to have had 28 million gallons of evaporation done by the cattails out there in that wetland. And we looked at those numbers and we're saying, sure, that's what the math says, why not? But prove it. Prove that the cattails are being that effective at helping to remove the excess water from that wetland. That the excess water that's being put in by the springs. The thing that keeps the water balanced. So to do that, we undertook a fairly, you can't, the idea is, I'll blow this up when it comes time to actually see something here. But the question really was, what can a cattail do? Can a cattail really be responsible for evaporating twice as much water from the wetland as the wetland is evaporating due to the sunlight and the temperature and the wind speed? You know, the things that normally cause evaporation. Can a cattail double that amount of evaporation? Can a cattail just suck the water out of the wetland and then evaporate it into the air? Is a cattail able to do that? So I can't make it too much bigger. So we went out there into the wetland and we planted these steel double-ringed, they're called infiltrometers, but they're just steel double rings. And they're planted into this thing. This one had 30, and we got the permission of the DNR to do this. We transplant, you guys can't start doing things with cattails. Cattails are protected. So we got permission to transplant 30 cattails into the inside of our ring. This ring, we also had permission to take the 15 cattails from there and transplant them over there. So we didn't actually kill any cattails. No cattails were harmed in this experiment. So anyway, we've got the cattails removed from this ring. We've got the cattails added to this ring. All we do is with a device, that's shown right here, to the 1/100th of an inch, we measure the change in the water level between here and here. And the previous student, who was before Max, would go out there and load water into this one, and then load water into that one. And we'd watch how the water level changed in one tank versus the other tank to see what is the difference. Because the only difference between this tank and that tank is the cattails. So the difference in the water levels between here and here would be due to the cattails. Are the cattails able to suck out twice as much water from this double ring as they're sucking out as the nature is taking out of that double ring up there? That was the question. This is the experiment. And Sleepy Eye's name did get shared and spread widely in San Francisco last December when we showed these results. So there are the actual physical results. Yeah, there was a lot of crappy math that was involved in doing this. But at the same time, you could show how the water level would fall when there was no cattails in the ring. And then you could see how the water fell when there was cattails in the ring. And that difference between here and here, and here and here, and here and here, that number is what we came up with using that map to show that those cattails around your wetland are right up here in this range. That number is 4.6 right up in here. Those cattails are actually absorbing 4.6 times more water than the type, just open water. So if it's just open water with sunlight and warm temperatures and the wind blowing on it, you'll get maybe this much water evaporated off of that wetland. Those cattails are evaporating that much water off of that wetland. It's incredible. It was a big hit out at the American Geophysical meeting in San Francisco last spring. They're really interested in these results because there's been a rate of those numbers can exist over a very wide range. And it turns out we're finding out that places like Florida and Georgia and places with cattails down there, they're the ones that get these really tiny numbers. Us, northern states, and that graph is actually from Montana. We're the ones that come up with the much bigger numbers. Our cattails are much thirstier here in the Northland than the cattails are down along the Gulf Coast area. That's something that we helped to uncover and add to the story, and Sleepy Eye is at the heart of helping to expand that story and that understanding of what cattails can do to a wetland. So the thing though here was about how we were worried about the water. One of the other things that we were very worried about was that mud and the algae. Because when we were out there doing our work, watching those double ring infiltrometers, we couldn't help but notice, you guys got algae blooms on your wetland. And the algae blooms are, in response to the nitrogen and the phosphorus, the carbon, the food stock that's being washed into the wetland. So what we wanted to know was if you do have a lot of, so 90+% of all the sediment that washes into this wetland stays in the wetland. 90% of all the phosphorus, 75% of all the phosphorus, 90% of all the nitrogen washing into your wetland stays in the wetland, feeding these guys. It's not leaving the wetland. So what's the long-term viability of your wetland? Is your wetland filling itself up quickly with the sediment and with all that stuff? The gooey algae and things like that that are growing in the water. We wanted to investigate that as well. So, with the help of Mary Beth's class, we went out onto the lake and we grabbed a core. We grabbed a sample from the bottom of the wetland, and that's the picture of one of the cores that we took from the bottom of the wetland. And I have written in the annotation next to the thing, just describing its attributes, not the least of which is that, we squeezed the thing hard, and we got a lot of that dissolved phosphorus. That's what TP stands for, phosphorus. So we got a lot of the phosphorus out of the water. We got a lot of nitrogen out of the water. That stuff is getting stuck in the pores in that muck. The muck itself is replete with carbon. It is those bits and pieces of those plants, those algae, the things that were in that water that were green are now black on the bottom of that wetland. That's not a bad thing, because those black gooey bodies are carrying with them that phosphorus and the nitrogen that have been washed into the wetland. So that's where those bottom numbers are listed there. In just the upper foot, the upper 12 inches of the core that we took, we estimate that you're looking at having 54,000 pounds of phosphorus buried in the bottom of that wetland. And you're having perhaps as much as 2,900 pounds of nitrogen. TN just stands for total nitrogen, but nitrogen buried in the bottom of that wetland. So you do have a receptacle for all that stuff that's washing in. It's the muck at the bottom of your wetland. The water we can account for. And all the water that washes in, some of it washes into the main lake, some of it gets evaporated, a lot of the water gets evaporated by the cattails. And now we can tell you the story about all the nutrient and the phosphorus nutrients, sediment and nutrients washing into your wetland. And that is, it's getting stuck in the bottom of your wetland. So what are you going to do? This is the point now where I stop talking and Kim and you all start talking, which is, what you going to do? You've got the perfect filter at the edge of your town. At current rates, we do not, I can't tell you, that's not what I can do. I can't tell you how long it's going to remain as the perfect filter at the edge of your town. You have to potentially use this sort of modeling, which the engineers can tell us more about, is about how long a wetland of that size and those dimensions are able or capable of performing at the high level that they're currently performing. And then, what might be the cost if you want that thing brought back after it does get filled up, after it is no longer functioning so perfectly, what might be your cost that it will take in order to get back to where it is now. Remember, again, please, one more thing. I'm always telling you everything as a function of drought. So my entire story always has to be shaded, well, he did all that work, but it was during a drought. Yes, that's true. I'm glad I have both hands in the air. Yes, accuse me, I did a drought study. So anyway, but during the drought, your wetland is working perfectly. It's absorbing all of the nutrients and all the sediment that you're washing into that thing, and it's not leaking, not from those sources, not into your main lake. So what are you going to do, sleepy eye, to make sure that you keep your wetland behaving the way that it is behaving currently? Yeah, I'm done.